Welcome to another deep dive. Today, we're peeling back the layers on something incredibly common, yet almost entirely overlooked.
Oh, yeah. What's that?
The complex world at the very top of a utility pole. We've got some absolutely fascinating source material here.
Ah, pole tops. Right.
Yeah, it lays out the mind-bending precision and, the engineering that keeps these essential structures standing and powering our lives.
It's surprisingly complex stuff for something we see every day.
Exactly. So our mission today is to really dig into the nitty-gritty of single-phase primary pole-top assembly units.
Okay.
We'll explore the surprisingly vast array of configurations they come in, the strict construction rules that govern their installation, and the deep engineering principles that ensure their stability and safety. It's kind of a journey into the unseen.
Revealing just how much thought goes into every single connection that brings power to your home.
Precisely.
What's truly fascinating here, I think, is how components that seem so mundane, so everyday, are governed by such incredibly detailed specifications.
Right. Not just poles and wires.
No, not at all. These aren't just poles with wires strung between them. They are highly engineered systems, designed to withstand immense forces while delivering reliable power day in and day out.
Okay.
We'll show you why every detail, like from a specific washer to a maximum line angle, is absolutely critical.
Okay, let's unpack this then.
Yeah.
When we talk about these pole-top assemblies, what exactly are we referring to?
Interesting.
What kinds of setups are out there, and why are there so many different kinds? It feels like it should just be, I don't know, one standard design.
You'd think so, wouldn't you? But at its core, we're talking about the entire collection of hardware and conductors.
Yeah.
All the bits mounted at the very top of utility pole.
All gear up there.
Yeah. Our sources provide this extensive index, various drawing numbers and their descriptions, revealing the sheer variety. It's like a specialized toolkit, really.
A toolkit? How so?
Well, each tool, each assembly type, is designed for a very specific job. Instead of one design, you have entire families of assemblies.
Families? Okay.
For instance, what are called single support units, like VA 1.1 and VA 1.2. They're designed for tangent lines.
Tangent lines, meaning straight sections.
Exactly, straight sections where the forces are relatively balanced. Then you have the more specialized VA 1.11, which is a single support on crossarm, providing the extra stability or height.
Okay.
And the P suffix you sometimes see, that tells you it uses post-insulators.
Post-insulator?
Yeah, they're rigid insulators that mount directly to the pole or crossarm, unlike, the hanging suspension types.
Got it. So we have designs for straight lines. But what happens when the line needs to, change direction or come to a complete stop?
Right.
That must introduce entirely different stresses, doesn't it?
Exactly. And that's where the engineering truly, it shines. For instance, there are double support units like VA 2.1 or VA 2.21.
Dual support.
They involve crossarms for greater strength, more capacity. And then, like you said, you have assemblies specifically designed for directional changes or endpoints.
Like corners.
Yeah, or dead ends. We have suspension angle units like VA 3.1, 3.2, 3.3 for turns that are less severe. And then more robust deadened angle units.
They're more robust. How?
Well, like VA 4.1, designed for sharp 90 to 150 degree turns. Or VA 4.2 for turns between 20 and 90 degrees. These are, marvels of force distribution.
Wow.
Our sources also detail various single deadened types, V5.1 through 5.4.
Single dead end.
Including those mounted on crossarms like VA 5.21 and 5.31. These are for the literal end of a line, handling just massive concentrated tension.
Makes sense.
And then there are double dead-end units too. V6.1 for straight lines, VA 6.2 for feed-through connections. Even those on crossarms like VA 6.21 and VA 6.22G.
It just keeps going.
It does. You even have specific guide components like the VA 1.12G single-phase junction guide or VA 5.5G single-phase tap guide.
Guide components.
Yeah, they manage where a line splits off or connects to another.
It's clear that each of these serves a very, very specific purpose in how the power line is structured. It's really not a one-size-fits-all approach at all.
Not in the slightest.
Every curve, every bend, every termination point, it demands a unique engineered solution to manage these, immense constant forces.
That's the key managing force.
Okay, so understanding the dizzying variety of these pole tops is just the first layer. The real marvel seems to lie in how they're precisely constructed, how they handle the forces of nature and, the demands of power delivery. Our source material highlights construction specifications for pole-top assemblies.
Right. The rule book.
What are some of those non-negotiable rules, the ones that ensure stability and safety?
Yeah, this section is where the critical details for safety and longevity truly come into play. One crucial specification, for example,
Go on.
it's that when you use high poles, maybe to clear obstacles like railroads, you must avoid upstrain on the insulators on adjacent shorter poles.
Upstrain. Okay, you mentioned that before. What does that mean in practice?
Right. Imagine trying to pull a string taut between, say, a skyscraper and a small house next door. The high point on the skyscraper could actually lift the strain off the attachment point on the house.
Yeah.
That lifting force is upstrain. And it prevents the line from damaging insulators or even, lifting shorter poles entirely. It's about ensuring the load is always pulling down on the insulators, not up.
That makes perfect sense for safety. But practically, how challenging is it for crews to implement that? Especially in, tricky terrain or when replacing just one pole in a long line?
Oh, it definitely adds layers of complexity for the field crews, which is precisely why these specifications are so meticulously detailed. There's not much room for error.
I bet. And what other fundamental rules are in place, say, for conductor placement?
Yeah, another critical one involves the neutral conductor. That's the wire that provides the return path for the current.
Okay, the neutral.
It has a very specific placement rule.
Oh.
It should always be installed on the same side of the pole, preferably the road side, for all tangent and small angle poles throughout the entire length of the line.
Always the same side. Why?
Standardization. It's key for consistency, safety, and honestly efficient maintenance. Crews know where to expect it.
Makes sense.
Interestingly, our source notes that prior RUS approval, that's the Rural Utilities Service,
Okay, RUS.
they set engineering standards for many power grids. Well, prior RUS approval can be given to lower the neutral attachment under certain circumstances.
Like when?
Maybe up to 2 feet lower, just to economically meet National Electrical Safety Code or NESC clearance requirements.
Oh.
Or even up to 6 feet lower for performant construction and future line maintenance from bucket trucks.
Practicality meets regulation.
Exactly. It highlights the, practical flexibility sometimes needed within these strict guidelines, provided it still meets all the safety standards, of course.
So those are rules for the overall line configuration and neutral placement. What about the immediate connection points? How are the main wires actually connected to the insulators on the pole?
The actual attachment. Well, the instructions are incredibly precise there, too.
I'm sensing a theme.
Definitely. With pin-type or post-type insulators, the conductor must be tied to the top groove when it's on a tangent pole.
Top groove, okay.
That ensures stability against sideways forces, like wind. But at angles, it's tied to the side of the insulator away from the strain.
Away from the strain. Why?
To keep the wire snug against the insulator, preventing it from pulling away under tension. And crucially, the insulators themselves must be tight on their pins or brackets.
Right.
And the top groove must be perfectly in line with the conductor after tying. No slop. And if you're using factory-formed ties...
Those pre-shaped wire things?
Yeah, exactly. They have to be installed exactly per the manufacturer's specs. No improvising allowed.
It's incredible how much thought goes into preventing just a single sag or weak spot, even in something as seemingly simple as a conductor tie.
Every detail matters.
Are there other unsung heroes? Maybe smaller pieces of hardware that play just as critical a role in preventing failure?
Absolutely. There are definitely unsung heroes up there. One is the 3-inch by 3-inch minimum square curved washer.
The washer.
Yeah, referred to as item D in a lot of the diagrams. This specific washer is mandatory, used abutting the pole when installing primary or neutral conductor deadened assemblies directly to the pole.
Okay, why a curved square washer? Seems specific.
It is. Its purpose is twofold. First, it mitigates the crushing of the wood fibers by distributing the immense pressure from the bolt over a larger area. Wood compresses, right?
Sure.
And second, it facilitates the allowable longitudinal loading. That's the pulling force along the wire given in the design parameters. Without it, the pole could be significantly weakened over time, leading eventually to catastrophic failure.
Wow. That's a great example of how a seemingly tiny detail, a washer, can have a huge impact on structural integrity.
It really is.
What about things that keep the entire assembly from, vibrating loose over time? Wind, traffic, just the electricity itself.
Great point. And speaking of structural integrity, a lock nut is mandatory.
Lock nut, like on furniture assembly.
It's sort of, but heavy duty. It's required with every nut and eye nut on all machine bolts, upset bolts, double arming bolts. Also, other threaded hardware like insulator pins and studs.
Everywhere, basically.
Pretty much. This ensures that the connections remain secure under constant load and vibration. Imagine, like you said, wind, temperature changes, even just the hum of electricity.
Right.
Over time, things can work loose. These lock nuts prevent that slow creep towards failure. It's another one of those unsung heroes holding everything together.
So far, we've seen the incredible variety and the precise rules for building these pole tops, but the truly fascinating part, for me anyway, is the deep physics behind why these lines stay up.
Ah, the engineering calculations.
Yeah. Our source material includes a series of tables that talk about maximum line angles on pin insulator assemblies.
This sounds like the very backbone of power line stability.
It really is.
Can you help us unpack what these complex numbers are actually telling us?
Sure. If we connect this to the bigger picture, these tables are essentially the engineering limits.
Yeah, the limits for how much of an angle a power line can make at a particular pole using pin insulators while remaining safe and stable. Think of them like a bridge's design specs.
Okay, like load limits.
Exactly. They tell you the absolute maximum angle a power line can safely make based on how much sideways force, what engineers call transverse loading.
Transverse loading, like wind pushing sideways?
Precisely, like a really strong crosswind, or even the pull from the conductor itself when it changes direction. It's the force it will experience on the insulator pins.
Okay.
These values are specified by RUS, the Rural Utility Service we mentioned,
All right.
and they incorporate appropriate overload factors from the 1997 edition of the NESC, the National Electrical Safety Code. That's a foundational safety document.
So it's all tied back to safety codes.
Absolutely. And the allowable longitudinal or transverse loading values you see. They're derived from known material strengths with NESC safety factors already applied.
Meaning they account for both the pull along the wire and the pressure across it?
You got it. Both directions of force are considered.
So these angles aren't just picked out of thin air, they're deeply rooted in physics and safety standards. It's about knowing the absolute limit before something, breaks.
Precisely. It's all about preventing failure under predictable and even some unpredictable stresses. We have 5 tables here, each one corresponding to a different designated maximum transverse load on the conductor.
5 tables.
Ranging from 500 pounds all the way up to 2,000 pounds of sideways force. That's the maximum force the insulator pins themselves are designed to withstand from the side.
2,000 pounds. That's a lot of force on one pin.
It is. And within each table, there are different variables at play that really refine that maximum angle, right?
Yeah.
It's not just one number.
Okay, what variables?
Yes, absolutely. For any given transverse load, say that 500 pounds, the maximum line angle you can actually achieve is profoundly influenced by 3 main factors. Each adds a layer of complexity.
Factor 1.
One is windspan. This is simply how far apart the poles are, measured in feet. Often ranges from, say, 150 to 400 feet.
Okay, the distance between poles.
Right. A longer span means there's more conductor between poles, which means more potential load on that insulator from wind or ice.
More wire, more force.
Exactly. So that means a smaller allowable angle to maintain stability. The further the gap, the less you can bend the line safely.
Makes sense. Factor 2.
2 is conductor size. This refers to the type and gauge of the wire itself. You see codes like 4 ACSR 71 or 3336.4 ACSR 267.
ACSR, what's that stand for?
Good question. Aluminum conductor steel reinforced.
Okay.
It's strong steel strands in the core, wrapped in conductive aluminum strands on the outside. The numbers indicate the overall size and how many strands of each material are used.
Got it. So bigger wire, more force.
Generally, yes. Larger or heavier conductors typically exert more force, so they reduce the maximum allowable angle.
All right. And the third factor?
Number 3 is loading district. This is a crucial environmental consideration.
Loading district, like geographic area.
Exactly. Whether the line is in a light, medium, or heavy loading district, these districts account for different typical environmental conditions, mainly expected ice accumulation and wind speeds.
So climate matters.
Hugely. For example, a heavy loading district, maybe somewhere prone to severe ice storms and high winds, will have significantly lower maximum line angles for the same conductor and span compared to a light loading district.
Why?
Because the design must account for much more severe environmental forces acting on the line. More potential weight, more potential wind force.
So let's take an example. Looking at table I, that's for a 500 pounds per conductor transverse load.
Okay.
If you have, say, a 400-foot wingspan and you're using a 4 ACSR 71 conductor,
Yep.
In a light loading district, the table says you can handle an 11-degree angle.
Right, 11 degrees.
But if you're in a heavy loading district with the exact same setup, same span, same wire, that maximum angle drops dramatically to just 5 degrees.
That's right, less than half.
Wow. That's a huge difference for the same physical components just because of the expected weather.
It truly illustrates how the local environment, dictates the very geometry of the power line. These tables aren't just abstract numbers.
No kidding.
They are the backbone of reliable power delivery, dictating exactly where and how power lines can safely be built. It's a constant battle against the elements pre-calculated and engineered into the design.
So what stands out to you when you see how sensitive these angles are to something like the loading district?
To me, it underscores just how interconnected the design is with the real world it operates in. You can't just design a power line in a vacuum. You have to know the conditions.
What an incredible deep dive this has been into a world that, honestly, for most of us, is completely out of sight and out of mind.
Isn't it, though?
We've journeyed from identifying all those diverse types of pole-top assemblies to understanding the incredible precise construction specifications.
The rules of the road.
And finally, sort of decoding these complex engineering tables that dictate how much a power line can bend without breaking. It makes you realize how every single wire, every nut, every angle isn't random. It's a carefully calculated decision.
Absolutely. This deep dive truly reveals that even the most common elements of our modern infrastructure, things we barely notice, are built upon this foundation of rigorous engineering, detailed safety standards, and careful consideration of environmental factors.
Yeah.
The specific rules for neutral conductor placement, the purpose of that little curved washer,
Right.
or the lock nut on a bolt, these aren't accidental details.
No.
They are crucial design elements that ensure our power grids remain stable and safe, regardless of wind, ice, or the demands we place upon them.
It truly makes you appreciate the unseen work, the hidden complexity that goes into just keeping the lights on.
It really does.
So the next time you glance up at a utility pole, maybe take a second look, consider the silent, meticulously engineered world humming away at its top.
Well said. And maybe think about this too. Given the extreme precision required for these assemblies,
Yeah.
what other everyday structures or systems around you, things you take for granted every day, might have similar, equally detailed and unseen engineering principles, just quietly keeping them functional and safe?